Good day, engineers. I am your Tito engineer, and today we will discuss important board exam situational problems from May 2011 CE board exam in the hydraulics and geotechnical engineering subject. May 2011, hydraulics. Problem number 1. A closed conical tank has a bottom radius of 33 centimeters and is 50 centimeters tall. The tank contains 0.026 cubic meters of water. Number 1. What is the depth of water in the tank in centimeters? Number 2. What is the total volume of the tank in cubic meters? Number 3. How much water is required to fill the tank in cubic meters? This problem is included in the hydraulics topics, but as you can notice, the problem only involves calculation of volumes, which can easily be solved using our fundamental knowledge about solid mensuration. We begin by illustrating the problem. Taking note that in actual board exam, it is seldom that the examiner will provide illustrations, so we have to do it on our own. For our solution to the second part of the problem, take note that we cannot proceed with the first part of the problem since we need to determine first the total volume of the cone as what is asked in part 2. Carrying on with our solution, the volume of a cone from our solid mensuration is equal to 1/3 pi r squared times the height. Substituting, that is, 1/3 pi 0.33 meters squared times 0.5 meters. Take note that we converted all of the units to meters since it is the required unit for part 2 of the problem. We will result to a volume of cone equal to 0.057 cubic meters. For our solution to the third part of the problem, the required volume to fill the tank in cubic meters is just equal to the total volume of the cone minus the volume of water already placed in the cone. That is, volume required is equal to volume of cone minus volume inside. Substituting values, we get volume required is equal to 0.057 cubic meters minus 0.026 cubic meters, or volume required to fill the tank is equal to 0.031 cubic meters. For the last part of the problem, we will be using the ratio of similar solids. We can divide the cone into two similar cones, one with a height of 50 centimeters and a radius of 33 centimeters. The other one will have a height equal to 50 centimeters minus h and an unknown value for radius, which we will not specify since it is not necessary. We already determined the following. Volume of the cone, the volume required to fill the cone, and the volume of water already inside the cone. By ratio of similar solids, volume of the cone over volume required is equal to 50 centimeters over 50 centimeters minus h cubed. Substituting values, 0.057 cubic meters over 0.031 cubic meters is equal to 50 centimeters over 50 centimeters minus h. Take note that we do not need to convert our 50 centimeters into meters since the units will just cancel out. By using shift solve function of our calculator, we can get h equals 9.18 centimeters as our final answer. Problem number 2. Water is flowing in a 200 millimeters diameter rigid pipe that is 850 meters long. The increase in pressure caused by instantaneous closure of the valve near the exit is 700 kilopascal. Bulk modulus of elasticity of water is 2.07 times 10 raised to 9 pascals. Number 1. What is the Ciel-Righty of pressure wave in meters per seconds? Number 1. What is the maximum discharge in cubic meters per seconds? Number 1. What water hammer pressure is expected if the valve is closed in 3 SECS? In this problem, there is no need for us to have a detailed illustration since this problem is formula-based problem. We can illustrate this one, but it is already not necessary to do so since it will just take time. For our solution to the first part of the problem, Ciel-Righty has a formula of the square root of bulk modulus of elasticity over the mass density. Ciel-Righty is a velocity, therefore it will have the unit for velocity of meters per second. Substituting the values, square root of 2.07 times 10 raised to 9 pascals over 1000 kilogram per cubic meter, we will get Ciel-Righty is equal to 438.75 meters per second. For our solution to the second part of the problem, we will use the formula for discharge, which is equal to area times velocity. We can solve for the area using the given dimension in our problem, but we need to identify first our velocity. From the given data above, pressure due to instantaneous closure is 700 kilopascal. Take note that for instantaneous closure, the formula for pressure due to instantaneous closure is equal to mass density times Ciel-Righty times velocity. Using this formula, Pressure of 700 kPa is equal to mass density of 1000 kg per cubic meter times seal righty of 438.75 meters per second times the velocity. Solving for velocity, we will get velocity is equal to 0.4865 meter per second. Since we already got our velocity, we can now solve for our discharge. That is, Q is equal area times velocity, or pi over 4 times 0.200 meters times 0.4865 meter per second. Our maximum discharge is actually equal to 0.0152 cubic meters per second. For our solution to the last part of the problem, we need to know first what type of closure will happen to the problem. It can either be instantaneous, rapid, or slow closure. We need to identify the type of closure first since there are different formulas for water hammer pressure in each type of closure. We begin by identifying the time for the pressure waves to travel back and forth, which we can get by using the formula. TR is equal to twice the length all over the seal righty. Substituting values, we get TR is equal to 2 times 850 meters over 438.75 meters per second. TR therefore is equal to 1.181 seconds. As you can notice, the time it takes for the wave to travel back and forth is faster than the closing of valve. Therefore the closure is slower. The type of closure for this situation is a slow closure. For slow closure, the water hammer pressure is equal to twice the length times velocity times mass density over the time of closure. Substituting values, water hammer pressure is equal to 2 times 850 meters times 0.4865 meter per second times 1000 kilogram per cubic meters over 3 seconds. Our water hammer pressure therefore is equal to 683.33 pascals or 275.683 kilopascals. Problem number 3. A rectangular canal is 5.6 meters wide and 1.2 meters depth. The canal is laid on a uniform slope of 0.002 and a roughness coefficient of 0.013. Number 1. Calculate the discharge in the canal in cubic meters per second. Number 2. What savings in lining per meter length of canal could have been affected if the most efficient rectangular section were used for the same discharge and slope? Number 3. What savings in earth excavation per meter length of canal could have been affected if the most efficient rectangular section were used for the same discharge and slope? We begin by illustrating the problem. Taking note that in actual board exam, it is seldom that the examiner will provide illustrations, so we have to do it on our own. For our solution to the first part of the problem, discharge has a formula of area multiplied by velocity. For this particular problems and for most of the problem involving open channels, we will be using the Manning's formula. Another hint, since it is not directly stated in the problem, is the use of roughness coefficient, which can be directly attributed to Manning's formula. Discharge will now be equal to area multiplied by 1 over the roughness coefficient times hydraulic radius raised to 2/3 times slope raised to 1/2. We will first solve the area, which is just the area of rectangle equal to base times depth, or 5.6 m by 1.2 m equal to 6.72 square meters. Next, we will solve for the hydraulic radius, which has a formula of area over wetted perimeter. Take note that the perimeter we will consider is only the perimeter in contact with the fluid. Hydraulic radius is therefore equal to 5.6 meters by 1.2 meters over 2 times 1.2 meters plus 5.6 meters, which is equal to 0.84 m. Substituting values to our formula, we can get 0.6.72 square meters times 1 over 0.013 times 0.84 m raised to 2/3 times 0.002 raised to 1/2. Our discharge therefore is equal to 20.581 cubic meters per second. For our solution to the second and third part of the problem, the question involves the use of most efficient rectangular section. By definition, most efficient section is a section wherein, with the use of minimum materials or perimeter, our discharge is maximum. For most efficient rectangular section, base is equal to twice the depth and the hydraulic radius is equal half the depth. Area is equal to base times depth, but since base is equal to twice the depth for most efficient sections, area will now be equal to twice the depth times depth, or 2d squared. Hydraulic radius for most efficient rectangular section is equal to d over 2. In this particular problem, it is stated that only the discharge and the slope will remain constant, so we need to identify the depth of flow. We need to determine the area and hydraulic radius in terms of the depth. Substituting values, 20.581 cubic meters is equal to 2d squared times 1 over 0.013 times d over 2 raised to 2/3 times 0.002 raised to 1/2. Using shift solve function of our calculator, we can get the depth equal to 1.794 meters. Finally, we will compare original values to our most efficient section values. Since base is equal to 2d, we get base equal to 3.588 m. For our original perimeter, perimeter is equal to base plus twice the depth or 5.6 meters plus 2 times 1.2 meters or equal to 8 meters. For our perimeter using most efficient section, perimeter is equal to base plus twice the depth or 3.588 meters plus 2 times 1.794 meters or equal to 7.176 meters. Savings in linings therefore is equal to original perimeter minus mass perimeter times 1m or 8m minus 7.176 m times 1. Savings in lining therefore is equal to 0.824 square meter per meter length. For our original area, area is equal to base times depth or 5.6 meters times 1.2 meters or equal to 6.72 square meters. For our area using most efficient section, area is equal to base times depth or 3.588 meters times 1.794 meters or equal to 6.437 square meters. Savings in earth excavation therefore is equal to original area minus mass area times 1m or 6.72 square meters minus 6.437 square meters times 1. Savings earth excavation therefore is equal to 0.283 cubic meter per meter length. Problem number 4. A pump draws 24 liters per second of water from reservoir C and lifts it to reservoir D as shown in figure. The head lost from C to 1 is 3 times the velocity head in the 150 mm suction line, and the head lost from 2 to D is 25 times the velocity head in 100 mm discharge line. Calculate, number 1. The power delivered by the pump to the system in HP. Number 2. Pressure head at 0.1 in meters of water. Number 3. Pressure head at 0.2 in meters of water. In this particular problem, it is clearly stated that we will be having a figure, so no need to illustrate the problem on your own. For our solution to the first part of the problem, we first need to establish the energy equation of the whole system. That is the energy equation between reservoir C and D. Take note that as stated in the problem, we will a head loss, therefore the values that we will get in the equation will all be actual values and not theoretical values. We also have to take into consideration the head that will be added by the pump. We begin. Energy at C minus head loss from C to 1 minus head loss from 2 to D plus head added by the pump is equal to the energy at D. Energy equation, as we all know, is composed of the potential and kinetic energy head, namely, velocity head for kinetic, pressure head and elevation head for potential. Energy at C is equal to velocity head at C plus pressure head at C plus elevation head at C. Head loss from C to 1 as stated in the problem is thrice the velocity head at the 150 mm suction line, or the velocity head 1. Energy at D is equal to velocity head at D plus pressure head at D plus elevation head at D. Head loss from C to 1 on the other hand as stated in the problem is 25 times the velocity head at the 100 mm discharge line, or the velocity head 2. For the values of velocity heads, velocity head 1 is equal to V sub 1 squared over 2g, but since we are given with the discharge of 24 liters per second or 0.024 cubic meters per second, we can use an alternative derived equation in terms of Q, that is, 8q squared over pi squared times gravity times diameter raised to 4. Substituting values, we get 8 times 0.024 cubic meters per second squared over pi squared times 9.81 meters per second squared times 0.15 m raised to 4. We get velocity head 1 equal to 0.094 meters. We will be using the same formula for velocity head 2. Substituting values, we get 8 times 0.024 cubic meters per second squared over pi squared times 9.81 meters per second squared times 0.10 m raised to 4. We get velocity head 1 equal to 0.476 meters. From our energy equation, we have to take note that point C and D is at the water surface of the reservoir. And since it is exposed to the atmosphere, the gauge pressure will be equal to 0, therefore, pressure head at C and D will also be equal to 0. Same for its velocity head, the velocity head at point C and D will also be equal to 0. We let this energy equation be our equation 1. We already solved the velocity head 1 and velocity head 2. To continue with our energy equation, we will solve for the head losses between C to 1 and 2 to D. Head loss from C to 1 is equal to thrice the velocity head 1 or 3 times 0.094 meters equal to 0.282 meters. Head loss from 2 to D is equal to 25 times the velocity head 2 or 25 times 0.476 meters equal to 11.90 meters. Substituting this values to equation 1, we will get the value for the head added by our pump, which is equal to 252.182 meters. Now to get the power delivered by pump, we will use the formula. Power is equal to discharge times unit weight times head added by pump. Substituting values, we get power is equal to 0.024 cubic meters per second times 9,810 newtons per cubic meters times 252.182 meters. This will result to a power of 59,373.73 watts. Since we are after for the horsepower, we will convert this one. In 1 horsepower, there are 746 watts. Therefore our power delivered by pump is equal to 79.59 horsepower. For our solution to the second part of the problem, we first need to establish the energy equation of the system from point C to point 1 in order to expose the pressure head at point 1, since that is what we are after. Take note that since we are after for the pressure head at suction side only, we can eliminate the head added by pump in the equation. We begin. Energy at C minus head loss from C to 1 is equal to the energy at 1. Energy at C is equal to velocity head at C plus pressure head at C plus elevation head at C. Energy at 1 is equal to velocity head at 1 plus pressure head at 1 plus elevation head at 1. Velocity head at point 1 as already determined before is equal to 0.094 m. Also, head loss from C to 1 is equal to 0.282 m. From our energy equation, we have to take note that point C is at the water surface of the reservoir. And since it is exposed to the atmosphere, the gauge pressure will be equal to 0. Therefore, pressure head at C will also be equal to 0. Same for its velocity head. The velocity head at point C will also be equal to 0. Substituting values, we get pressure head at point 1 equal to 19.621 meters. For our solution to the last part of the problem, we first need to establish the energy equation of the system from point 2 to point D in order to expose the pressure head at point 2, since that is what we are after. Take note that since we are after for the pressure head at discharge side only, we can eliminate the head added by pump in the equation. We begin. Energy at 2 minus head loss from 2 to D is equal to the energy at D. Energy at 2 is equal to velocity head at 2 plus pressure head at plus elevation head at 2. Energy at D is equal to velocity head at D plus pressure head at D plus elevation head at D. Velocity head at point 2 as already determined before is equal to 0.476 m. Also, head loss from 2 to D is equal to 11.90 m. From our energy equation, we have to take note that point D is at the water surface of the reservoir. And since it is exposed to the atmosphere, the gauge pressure will be equal to 0. Therefore, pressure head at D will also be equal to 0. Same for its velocity head. The velocity head